The topic is now neural architecture search. Neural architecture search is a subfield of machine learning focused on automating the design of neural network architectures. So the definition is it's a neural architecture search is the process of automating the design of neural networks to optimize the performance for a given task. The goal is to find the best performing architecture for a specific data set and task without manual intervention. Goal is to find the best performing architecture for a specific data set and task without manual intervention. It reduces human effort, accelerates model development, and may uncover novel architectures. The key components of neural architecture search, it typically involves three main components. The search space, it defines the set of possible architectures. All possible architectures can include hyperparameters, layer types, connections, etc. Convolutional neural networks, for example, convolutional neural for vision tasks, recurrent neural networks, or transformers for sequential tasks. Now, the types there's a fixed space, search space, predefined operations, and with predefined operations and fixed structure, and flexible search space, which allows for dynamic constructions of the architecture. So, search strategy, the method used to explore the search space. Common strategies include random search, randomly sampling architectures, then evolutionary algorithms, which uses genetic operations like mutation and crossover, then reinforcement learning. It treats architecture search as a sequential decision making process. Reinforcement learning, it treats architecture search as a sequential decision making process. Treats architecture as sequential decision making process. Bayesian optimization models that performance of architectures as a probabilistic function. Then gradient based methods optimizes architectures using gradients. Then grid search, exhaustive search over a fixed set of options. Neuroevolution combines evolutionary algorithm with neural network optimizations. So search space, search strategy, and performance estimation. Evaluates the performance of sampled architectures. Like methods of full training, the train and evaluate the method fully, accurate but expensive. Train and evaluate the method fully, accurate but expensive. Early stopping, stop training early if performance stagnates. Weight sharing, share weights across architectures to reduce training cost. So, sharing of weights across architectures to reduce training cost. Proxy tasks evaluate performance on a smaller dataset or fewer epochs. Now, search space design. So, macro search focuses on Search space design, macro search focuses on high level architecture design, number of layers, module types. Micro search optimizes low level building blocks, for example, convolutional or attention modules. Hierarchical search combines macro and micro levels for multi scale optimization. Search strategies, exhaustive search. Now, exhaustive search it tests all possible architectures. Heuristic search like genetic algorithms, hill climbing, then meta heuristic search, reinforcement learning, neural evolution, gradient based search, differentiable NAS, efficient and faster than traditional methods, and one shot NAS, neural architecture search, builds a supernet containing all architectures in the search space. Performance estimation techniques, training from scratch, evaluates architectures by training them fully. Then expensive and time consuming, which are this is expensive and time consuming. Then weight sharing reduces computational cost by reusing weights across architectures. Then predictors based method estimation uses a predictive model to estimate performance. Surrogate models approximates architecture performance using statistical models. This is also very interesting. Now, challenges in NAS, neural architecture search. The computational cost, NAS is often resource intensive, requiring significant compute power. Solutions are weight sharing, early stopping, proxy tasks. Search space design, poorly designed search spaces can limit the discovery of optimal architectures. Now, poorly designed search spaces can limit the discovery of optimal architectures. Overfitting to proxy tasks. Architectures may perform well on proxy tasks but fail on real world tasks. This is an interesting problem. Architectures may perform well on proxy tasks but fail on real world tasks. Scalability, different scaling NAS, difficulty scaling NAS to very large dataset or tasks. Interpretability, NAS generated architectures may be complex and hard to interpret. Reproducibility, results can vary significantly due to randomness in the search spaces. Now, types of NAS algorithms, reinforcement learning based NAS treats architecture search as a sequential decision making problem. Evolutionary algorithms uses principles of genetic evolution, mutation, selection, crossover. Differentiable NAS models the search space as a continuous function for gradient optimization. Models the search space as a continuous function for gradient optimizations. Models the search space as a continuous function for gradient optimization. Models the search space as a continuous function for gradient optimization. Models the search space as a continuous function for gradient optimization. This is differentiable NAS. Then Bayesian optimization models the relationship between architecture and performance using a probabilistic framework. Neuroevolution combines evolutionary algorithms with neural networks. One shot NAS builds a single supernet and shares weight across architectures. So, this is very, very interesting. Now, one shot NAS is builds a single supernet and shares weights across architectures. Applications of NAS: computer vision, image classification, object detection, natural language processing, machine translation, sentiment analysis, reinforcement learning, reinforcement learning. So, image classification, object detection. Hmm. Natural language processing, machine translation, sentiment analysis, reinforcement learning, optimizing policies, time series analysis, forecasting and anomaly detection, disease detection, drug discovery, designing lightweight models for mobile and IoT devices. Popular NAS frameworks and libraries: Autokeras. It simplifies NAS for general users. Then Google Visor, a tool for hyperparameter tuning and NAS, neural network intelligence open source framework for NAS, TensorFlow model optimization toolkit supports NAS for mobile and edge development, PyTorch Lightning plus NAS integrates NAS into PyTorch workflows. Notable NAS architectures: NASNet, reinforcement learning based NAS for image classification; AmoebaNet, evolutionary algorithm based NAS; DARTS, differentiable NAS for efficient architecture search; differentiable NAS for efficient architecture search; efficient net combines NAS with compound scaling, reduces computation by weight sharing. Future directions: scalable NAS, developing methods to scale NAS to larger datasets and more complex tasks, designing architectures suitable for multiple tasks simultaneously, optimizing architectures for reduced power consumption, estimating architecture performance without training, improving the explainability of NAS generated architectures. So, by automating architecture design, NAS has the potential to significantly advance deep learning, making it accessible to a wider audience while discovering novel and efficient architectures. Thank you very much.